Hi, I hope that all of you are doing great, especially on these hard days being affected by coronavirus. I hope that neither one of you nor your beloved ones have been affected by this virus in any ways. On this video, I want to continue my lesson for factoring polynomials. In this video, I will introduce four other techniques and methods for factoring polynomials. This is the third lecture that I am talking about this subject, and this is lecture number 13 on the series of lectures under the title of Advanced High School Algebra. If you have been following my YouTube channel, probably you know that there is a playlist under the same exact name, Advanced High School Algebra. After this lesson is finished, I will upload this video onto that playlist. Below the video, you will find 5 links. The first link, as usual, will take you to a PDF file containing a number of problems. I have partitioned the problems into 2 groups. The first group contains those problems and exercises that in principle you are able to solve them based on the material that will be covered in this lecture. But the second part contains some problems, a little bit harder. Sometimes I call them challenging problems. They have been chosen in a way that you need more or less all your knowledge, even from the previous lectures. My intention to have those problems in the problem sheet is I want you to be engaged more on the problems and provide you with this opportunity that you can remember them and don't forget what you have learned so far. And I have chosen those problems a little bit harder because, first of all, this is the second round that you are going to solve the problems from those lectures. So you have a little bit more experience with you now. So in principle, you are capable of solving harder problems. The other thing is that if the problem is a little bit harder, first of all, it is more fun. When you solve a harder problem, you enjoy more than when you solve a simple problem, of course. And the other benefit is that when you want to solve a harder problem, you have to be engaged with the problem for more number of hours. And then it means that sometimes you have to review what you have learned from the previous lectures. You need to probably Google a little bit around to understand what's going on. All these processes will provide you with the opportunity to deal with the problem for more number of hours, and then it will help you to transfer all these knowledge from probably your short-term memory to your long-term memory, and then you will have that knowledge with you all your life. And if you want to deal with mathematics or any major in the university related to mathematics, then it would be very helpful for you in the future. Okay, now let me explain you about other links. As you see on the screen right now, so this would be my lecture note. I will follow these notes and examples and everything written in this lecture note. So if you see here, for example, I am describing some important points about this lecture, and then you can see that I have some examples, and then here I have a little bit of empty space. During the lecture, during this video, I will try to solve those problems for you here and explain them. Okay, I have provided one, and then you see that I can go to the other pages, more or less the same structure, other pages. So I have provided you a link below this video. If you are interested, you can download the PDF version of this lecture note, as well as the GoodNotes version of these lecture notes. Okay, because I am actually making these videos by using my iPad Pro and Apple Pencil, and I'm using the application called GoodNotes version 5 to produce these notes. Okay, so the benefit of those links from my point of view is that you might be able to print these pages out and then put them in front of you when you are watching the video, and then you can write your own notes on these papers. And then, for example, when I come to these examples, you can pause the videos and try to solve the problems yourself. Probably not the first one, and the second one you need to wait for me to explain it a little bit for you to understand what's going on. But for example, from problem number 3, you can pause the video and try to solve it yourself, and then you will have this empty space. You can fill it up here, and then you can play the video again and check your answers against my answers. And for those of you that, if in any case you have access to some tablet with GoodNotes installed on it and you have a pen, I have also provided you another link that you can download the GoodNotes version of this file, and then you can immediately download this file immediately directly onto your tablet, and then you have this point, and then you can start writing everything that you need directly on your tablet. And then after the video is finished, then I will have written all the detailed solutions for these examples. Then I will also provide you with 2 more links. One link takes you to the PDF file version of this lecture note, but this time the solutions are also included. And the other link will take you to the GoodNotes version of the same thing. Okay. Now, if you remember, I have already talked about 2 different methods for factorizing a given polynomial. One method was factoring out, if possible, a common term, which is common to all the terms in the polynomial. Yes, of course, this is not always the case that all the terms in the polynomial share a common factor, but if possible, I can take a common factor out from all the terms in the polynomial. And I already told you that this method will have the priority over all other coming methods. And then the second method we learn is that we learn how to use famous identities, algebraic identities, to factorize polynomials. Yes, and now I want to talk about the third method today. I have called it grouping and factoring out. So still I want to factor out, but sometimes it is not possible to factor a term out from all the terms in the given polynomial. The reason is that we don't have that common factor common to all the terms. But if we partition the terms in the polynomial into separate groups, in each group I can factor a common factor out. And then when I do this in each group, then I will see that a new factor, which is common to all the terms in the polynomial, emerges. And then I can factor out that new factor out. Then it will give rise to a factorization of my polynomial. Yes, so I want to describe this for you with very simple examples here. So here, I hope that you have the printed version of this lecture notes in front of you, or you have already downloaded it onto your tablet, and then you can immediately start solving the examples with me. The first and the second one, it's good to listen to me what I mean by this method, and then if I were you, I would pause the video and try to solve the rest of the problems myself first, and then play the video to see that if you have done it in a correct way. So mathematics, of course, you will gain something just by watching the videos, but not that much. To be honest, you need to be an active learner, not a passive learner. By just listening to the videos, you will not benefit a lot. You need to be really engaged in the process yourself. Okay. Okay. So let us go and see here. So problem number 13. So let me divide this into 2 parts so that I can write here for you. Yes. Okay, so now we can start solving the first problem. So what is the first problem? So here, if you see, you cannot see any common factor which is common to all the terms, yes? So for example, A, if you want to consider A, only these two terms contain A. If you want to consider C, only these two terms contain C. And if you want to consider B, only these two terms. And if you want to consider D, only these two terms. Okay, so it is not possible to factor a common factor out from all the terms, because this is not the case here, that all the terms share a factor in common. So what I do, I try to group them, partition them into separate groups. In each group, I should have at least one common factor. But most importantly is that when I factor that single term, that single factor out in each group, a new common factor, which is common to all the terms for the polynomial in its new form, should be in common, okay? Should emerge. So let me, for example, tell you what we can do. For example, here, if I want to write problem number 1, so one way of dealing the problem is that I can take AC and AD together, yes, because they share a factor of A. And then let us take these two terms together, okay? So what can I do? Between these two, I can factor A out and write this. So it becomes A, and I will have C plus D. And now between these two terms, between these two terms, I can factor a B out. Yes, is that clear? So I can factor a B out. So then what happens? It becomes B, and what is left for me from the third term is C. What is left from the last term is D. Okay, but now do you realize what I meant here? You see, now when I look at here and here, I see a new common factor which is common to all the terms emerges. And that is this factor C plus D, which is common to both terms. So I can simply take C plus D out. And now what is left from here? I am pulling C plus D out. What is left from this is just A, and what is left from this is positive B. So what I write is that I write A plus B. So this is one way of grouping the terms, and that was quite successful. Because after factoring that common term in each group, a new common factor, which is now common to all the terms, emerges. Here in this case, it was C plus D. But of course, probably this is not the only way of grouping the terms in this polynomial. For example, let me change my color here. I might be, I don't know, you might take this one with this one, targeting common factor C, and you can take this one with this one, targeting common factor D. Let us see that if this is also possible. If I want to take these two, you see that C is a factor in common, okay? So I will take C out, then what is left from the first one is A, and what is left from the third term is B. Plus, between the other, in the other group, I can factor D out. Yes, so this becomes D, and then it becomes A plus B. So this is also considered to be a good grouping, partitioning. Why? Because now a new common factor, which is common to all the terms, emerges. This time it is A plus B. So what can I do? I can pull A plus B out now, then I will get C plus D. So, and then you see that they are exactly the same. So this is a factorization of this polynomial, okay? So let me try to explain the other one for you, okay? So what is the other one? So let us see here. Number 2. Let me explain everything once more. Okay? So for example, I can do this. I can take this one with that one. Okay? Why? This is a good choice, or a possible choice, I would say, because at least you see that there is a factor common to these two terms, and that is 3x. And then let me take these two together. Okay? This is also good. Why? Because there is a common factor for these two terms, and that is 2y. Yes. So now let us see that if it is actually working or not, because even though this is important to realize how to group them, but the important thing is that after you factorize the common factor in each group, you should have done it in a way that you can see that a new common factor actually emerges. If not, you need to throw that grouping away and then do another one. So in the first few problems, you have to do some trial and error, but little by little, when you increase your skill and experience, probably you will be able to solve these problems immediately. And I have to tell you that if the question is if the polynomial involves very many terms, even for me and probably for everyone else, it might be very hard to realize what to do. But at least these are standard problems that you might face in exams and in other books. And if you're studying on yourself, probably this will help you. You shouldn't expect too much hard problems, yes, because factorizing polynomials in general has is a very lengthy process if you want to do it algorithmically. Okay, so let us consider number 2. So number 2, I would consider these two terms. These two terms have 3x in common. So let me factor 3x out. Okay. And then what is left? From the first one, 2a is left. And from the second one, minus 3b is left. Yes. It's not still clear that I have done it in a correct way. I need to check the other one as well. If there is a common term emerging, then it means that this grouping was actually correct. Okay, so let us do the other one as well. So between these two terms, I will factor 2y out. So then I will have 2a left from the third term, and minus, I will have 3b left from the last term. So now you realize that my grouping was indeed a good one, yes? Because now you see that this common factor now emerges. And I can pull this out, and then it will give rise to the factorization of my polynomial. So I will take it out right now, so it becomes 2a minus 3b, then I will have 3x plus 2y. And that is the way that I factorize my polynomial, yes. So for example, you might think that I can take, so for example, can I take this one with that one? Yes, in principle, there is only one common factor between these two, and that is 6. But if you take 6 out, what is left is ax minus by. This would be your new factor. But then there is no way that you can pull out that factor here. So this is not a good grouping. But for example, you might think that this is also possible if I take this one with this one, and I take these two together. Okay. I don't know, sometimes this software stopped working. So let me stop sharing and do it once more. Sorry, I don't know what is happening sometimes. Probably I have to change the software that I am using. Okay, now it's working now. Okay, so so now I take these two together, and these two together. Yes, let us see that this will work or not. Okay, so if I take these two together, 6ax, 4ay, and then you can immediately see that I can pull 2a out. So what is left from the first one is 3x, and what is left from the second one is positive 2y. Yes. But here, between these two, if I just factor 3b out, so let me just factor 3b out, then what is left? From the first one, minus 3x is left, and from the last one, minus 2y is left. Okay? So, but now you see that the factor that emerges here is 3x plus 2y, and the factor that emerges here is minus 3x minus 2y, yes? But they are not the same, so I cannot say that so far it has been successful. But the difference between this one and that one, now I hope that you have some experience from the previous lectures, is that the only difference here and there is that the second one is with the wrong term. Here, what do I mean by the wrong term? It means that if I factor a minus sign out, okay, then everything will be fixed. So what I'm saying is that you could just write this one, but instead of pulling 3b out from the second group, I can pull minus 3b out. Then what will be left here? It would be positive 3x and then positive 2y. So this is still good, yes, because I can factor 3x plus 2y out now, and then I will have 2a minus 3b. So you see that this grouping is also successful because it gives me the correct solution. Okay. So now I really suggest you to pause the video and try to solve the problems 3, 4, 5, and 6 yourself. And then after you are done, play the video again and try to see that if you have done everything right. Okay? Now I'll go to problem number 3. So number 3, let us look here. First of all, in number 3, I hope that you remember a remark that I gave you in the first part of the lectures for factoring polynomials. I told you there that if you can factor, if there is a term which is common to all the terms, before thinking which method is suitable for doing this, for factorizing this polynomial, remember, you need to pull that common term out, and then you have the factorized form, and then think which technique would be suitable for the factors involved in its new form. Okay, so let me see here. You see, between this, and this, and that, we have x squared in common. So if I want to think about factorizing this polynomial, I immediately pull x squared out, and then I will try to see what can I do with what is left now. Okay, so what I do, I take x to the power of 2 out. I take x to the power of 2 out. So what is left from the first one is x3 minus x2 plus x and negative 1. Yes. So as you see, this is already in a factorized form, but probably it is not fully factorized yet. This is in the factorized form because you see that this is now a product of two factors. One of factors is x squared, and the other factor is this long polynomial. But can I go further and factorize this factor more? So this is already factorized because x to the power of 2 is just x, and I cannot do anything with this factor. So the only thing that I need to be worried about is that, is it possible to continue with this one and factorize it even more? Then this method that I taught you so far will help you to do that. And I hope that you have a little bit of experience by now. So what I do, I will take these two together, I group them together, and then I will group these two together. Okay, so the first part, I will actually write x squared, and then between these two terms, this one and this one, I can factor x squared out. So it becomes x squared times x minus 1. And then you see immediately the second terms, x minus 1 is exactly x minus 1. So I don't need to factorize anything. That's the common factor. So what I do, I just put them in a pair of brackets, x minus 1. So this is good. Why? Because now you can see that there is a common factor that is involved here. So I can pull it out again. So x squared is already there. I put x minus 1 out, so it becomes x minus 1. And then what is left here, x minus 1 is pulled out. So what is left is x squared. And then x minus 1 is pulled out. So what is left here is positive 1. Because when we factorize, we are actually dividing these terms by the common factor that we pull out. Yes. So what happens? The first one becomes x squared, and the last one becomes y. Okay. And hopefully you know that this cannot be factorized more unless we are working in a set of complex numbers. And I told you by default, we always consider that we are factorizing on the set of integers z. Okay. So I would say that this is the end of the story here. So this is the fully factorized form of that given polynomial. Okay, so let us go to number 4. So in number 4, you see that I have 6 terms involved, but that's quite simple. The reason that I brought this example in, because I wanted to tell you that there is no necessity that you have to partition the terms into groups of containing two terms. Yes, it might happen that you partition them into groups containing more terms. So for example, you can partition them in here, I can partition them into 2 groups, each group containing 3 terms. And that's very easy to guess here, I would say. Yes, you can immediately see that these 3 terms actually have a squared in common, and these 3 terms have minus b squared in common. So that's very clear what to do. So I will take this one, and this one, and I will pull a squared out. So number 4, I will pull a squared out. Then I will have x plus y plus 2. Yes. And then I will take these 3 together, and then I will pull out minus b squared. Yes. If you just pull b squared out, then you will get a factor with the wrong term. Yes. So you have enough experience by now. So I will have minus b squared out, then I will have x plus y plus 2. Is this a good partitioning? The answer is yes. This is a good partitioning. So what I do is that I can pull x plus y plus 2 out. X plus y plus 2 is now a new factor that emerges, and it is common to all the terms. Yeah, so this grouping, I would call it successful. So then it becomes x plus y plus 2. Then I have a squared minus b squared. Okay? But if you stop here, of course, this is already in factorized form. It is written as a product, but this is not a complete form because hopefully you can immediately recognize this pattern. It's a conjugate pattern. So if I stop here, that's not complete. I have to continue. So the answer would be x plus y plus 2, and then I will factorize the second term using the conjugate pattern. So it becomes a minus b times a plus b. So that is the final form for factorizing this polynomial. Okay, so now let us go to number 5. So problem number 5, here you see, for example, if you choose to take this one and this one together because you see b is in common, then you will not have any common factor here. Okay, you might say that, okay, I will pull b out from this, it becomes a plus c, and then I can factor a b out, so it becomes b squared plus ac. But you see that there is no common factor emerging now. So this grouping, even though might be possible, but this is not working. So you need to forget about it and to try to do in another way. Yes. So what are the other options? For example, one other option that might be easy to see is I take this one with this one, I take this one with this one, and I will take these two together. Yes. So here, between this one and this one, I have a factor b in common, so I can pull it out. Yes, so it becomes b. It becomes b, and then what is left from the first one is a, and what is left from the third one is negative b. Okay, but then I will take this one and that one, and I see that there is a c, there is a factor of c here. But if I just naively factor c out, then I will have b minus a. Again, you see the same situation happens. In this form, I don't have any common factor. Yes, the factors for this term is b and a minus b. The factors for this are c and b minus a. So b and c are not in common. A minus b and b minus a are not the same thing. But you know that the second one has again the wrong term. So you know you have experienced a lot for this kind of problems now. So you can have this one, instead of factoring c out, I can factor minus c out. So you really don't need to write this part. Yes. So you can start writing this as a solution. And then when I factor minus c out, what is left is a minus b, exactly the same factor that I need. So now I would consider this a successful attempt. Yes. So it becomes a minus b, and then it's b minus c. So you see now a minus b is a common factor. I pull it out and write it here. From this one, b is left. From this one, minus c is left. Okay, and finally, we go to the solution of this problem now, number 6. So here, for example, I don't know, probably we have 2 different ways. Which one you want to choose, that's up to you, but let me choose these 2 together, and then I will take these 2 together. Okay, so then from the first 2 terms, I can pull a out. I can take a out, and then I am left with a squared minus 4 in brackets. And then you see that a squared minus 4 doesn't have anything in common, so I just write them down. But this is a good way of doing that, because a squared minus 4 itself now plays the role of the common factor. So I will consider this a successful grouping. Yes. So then I will take a squared out, a squared minus 4 out, and what is left from the first one is just a. And because I pulled a squared minus 4 out, what is left from the second one is just positive 1. Yes. But of course, I hope that you will realize that the first factor is itself in the form of a conjugate pattern. So I have to use it and continue my factorization. So it becomes a minus 2, a plus 2, and then I have a plus 1. Yes? Okay. So I hope that you also learned this technique. So this is now in your toolbox. Sometimes you need to factorize some polynomials with this grouping and factoring out. And these are some examples. I will also provide you with more problems in the problem set that you will have the link below this video. So I don't know, sometimes the software that I am using freezes and it doesn't work, so I have to shut it down and open it again. Okay, sorry for that. Okay, now this time we want to actually solve this problem. So let us do it together. Okay, so here, problem number 1. So here you see the previous method is not working here. So let me look at this problem here. I have x squared plus 2x minus y squared minus 2y. Okay, so here you might think that, okay, first of all, you see that there is no term which is common to all the terms. And this on its own doesn't follow any pattern related to any identities we studied so far. Okay, And then, of course, you might say that grouping might work here. So let me tell you why this is not working. For example, you might say that I will group these two together because they have a factor of x in common. And then you might think that you can have this in common because they have a factor of negative y, for example, in common. Even though you are right, but this doesn't work. Why? Because if I factor x from the first two out, then I will have x times x plus 2, yes? And if I factor minus y out from the second group, I will have minus y and y plus 2, yes? Everything that I have done so far is valid but useless. Why? Because now the first one, the factors involved in the first one are x and x plus 2. The factors involved for the second term, are y and y plus 2. So, but you don't have any common factor now. So no common factor emerges. So it doesn't work. So it means that the technique probably is not this old one. We need to know a little bit new techniques. A new technique, actually. Okay, so what we can do. For example, let me clean this because we're not going to do this. So let me clean this grouping as well. Another way to do this is probably try to take this one with this one, not because they share a factor of common, because they don't. Yes, x squared and y squared doesn't have any factor in common. Okay, and then group these two together. So let us see what happens. Let me write everything down patiently for you. So x squared minus y, I decided to put them into one group. So let me put brackets and write x squared minus y squared. And then I decided to put 2x and 2y in the first group. In the second group. Okay, but now what you see is this. X squared minus y squared can be factorized using an identity we very well know, and that's the conjugate identity. So let me just factorize it. So then the answer becomes x minus y times x plus y. And the second one can be factorized by factoring 2 out. Now you immediately see that this is a good way of dealing the problem. You see, now x minus y is a common factor to the whole expression, yes? And I can pull it out. So then what is left is x minus y, and then what is left is x plus y from the first one. So I am pulling x minus y out. From this, x plus y is left, and from the second one, positive 2 is left. Yes, but of course I don't need extra brackets, so I would remove these internal brackets, a pair of internal brackets here. So then I will have x plus y plus 2, and this is in the factorized form. So you see, still I am doing some grouping, but the philosophy of this grouping is different from the previous method. Here, I am grouping because I see a pattern of an identity. Here, x squared minus y squared, I group them in the same group because, not because they have a factor in common, because they follow the pattern of conjugate identity, so that if I use the identity, conjugate identity to factorize it, then a new factor common to all the terms will emerge. Okay? So let me try to solve the second one for you as well. Okay? So number two, is x squared minus y squared minus 2x plus 1. Okay, so what can I do here? Can you see it yourself? So for example, these two, of course, follow the conjugate pattern, but let us see. If I factor it out, it becomes x minus y. If I factor it out, it becomes x minus y, x plus y, and then I have minus 2x minus 1 if I factor negative sign out, okay? But then you see that there is no common factor emerging. So it's not working. But now, let us see what happens if I take this one with this one and that one. What is happening now? Can you see the pattern? x squared minus 2x plus 1, and then minus y squared left alone. Okay, so what happens? Let me write it down for you here. So it becomes x squared minus 2x plus 1. Then I have minus y squared. But now what happens? Hopefully you can immediately recognize this pattern. That is a quadratic pattern. So it becomes x minus y to the 2, and then I have minus y squared. Yes? So I would consider this grouping a successful grouping, because now if you see that a new pattern emerges, you see in the previous problem, after I used the conjugate identity, I found a common factor. This time I use these three to make the quadratic pattern, but there is no common factor emerging. The good point here is that the pattern that emerges here is a conjugate identity. So sometimes you use the identity and factorize it, and then you find a common factor between the first group and the second group. Sometimes you collect the terms, and your goal is to collect them using an identity, and then when you do that, instead of finding a common term, you will find another pattern which follows the same identity or one of the other known identities. This is one of those examples. So what I can do, I can continue. I would factorize this using the conjugate pattern. So the square root of the first one minus the square root of the second one times the square root of the first one plus the square root of the second. We have trained ourselves about these kind of questions on the previous lectures related to factoring polynomials. But then you realize that in mathematics, we do not write extra brackets if they are not actually necessary. So here in this case, I don't need them, so I remove them. So then it becomes x minus 1 minus y, but if you want to write in an organized way, I prefer to write x minus y minus 1. Of course, it doesn't matter that much. And then the second one becomes x plus y minus 1. And this is the factorized form of these polynomials. Okay, so now if I were you, I would pause the video and take my pen, or I don't know, Apple Pencil, depending if you have the PDF file or the GoodNotes version. You can think about number 3 and 4 yourself. And then after you are done, you can play back the video once again to check your answers against mine. Okay? Don't forget, you only learn mathematics if you really actively be engaged with the problems. Okay, now number 3. This might be a little bit more tricky. So I don't know, can you follow the pattern? So you need to see, this is why I'm saying that you need to be very well trained in algebraic identities. So you might have seen my previous videos. I have talked about algebraic identities a lot, and you know that mathematics is a very hierarchical subject. So if you don't understand the previous parts, your chances to fully understand what is coming next is very low, actually. So now, the only way that you can solve this problem is that you have already trained a lot when we were talking about algebraic identities. Okay. So let me remind you of that algebraic identity, which is important here in the first place. Okay, so let me write with this here. Let me change my color. So if you remember, we had this. We have x plus y to the 3. It's x to the 3, and then I have 3x squared y plus 3xy squared plus y3. This is one of those identities we studied actually extensively in one of the previous lectures related to algebraic identities. Here, if I change x with a, and if I change y with -1, let us see what happens. So then this becomes a minus 1 to the 3. So what I'm doing, I'm replacing x with a, I'm replacing y with minus 1. Then you immediately realize that this identity becomes a to the 3 minus 3a squared times 1. So you see minus 3a squared times negative 1, it becomes negative 3a squared. And then it becomes positive 3a. And then negative 1 to the power of 3 is negative 1. Okay, so you see that this is something. So this is what I expect you by just looking at the problem, you can realize that. Okay, so I hope that you now understand what is the goal. The goal is to take this one and this one, this one and this one together. Yes, and then it will give rise to this identity. So let us do that. And then minus b3 will be left alone. So number 3, so if I want to continue, I will group them in the same brackets, pair of brackets, plus 3a minus 1, and then minus b3 is left here. Yes. But then I can collect this, and I write it a minus 1 to the power of 3 minus b to the 3. And then if you see, this is the difference of cubes now. And again, I have talked about the difference and sum of cubes, complete cubes, a lot in the previous videos, so I can use that identity. But if you don't mind, let me remind you that identity here once more. So the identity was something like this. I have written it in this way: a to the 3 minus b to the 3, the difference of two complete cubes, is the cubic root of the first one minus cubic root of the second one. The first one to the 2, the product of the terms with the opposite sign, and then the second one to the 2. Yes. But now what is happening here, if I want to continue here, this plays the role of this a, and of course b is the same b. So if I want to use this identity, what I do, let me write it here, this becomes equal to the cubic root of the first one minus the cubic root of the second one. And then you have the first one to the 2, the product of these two with the opposite sign, and the second one to the 2. Okay, of course, here we do not just leave it like this. I don't need these pairs of brackets, so I just simply remove them. Then it becomes a minus 1 minus b, but I prefer to write it minus b minus 1. And the second one, I square it because no one will leave this factor as messy as this one right now. So I will try to simplify this factor on its own right. So I will square it, so it becomes a squared minus 2a plus 1. Then I will multiply the other ones. So it becomes ba minus b, and then I have b squared. Okay, so then what I get is a minus b minus 1. Then I will have a squared. So let me write ab here. Then I will have b squared. Then I will have minus 2a minus b plus 1. Okay. This is a factorized form of my polynomial, of course. Okay, so there is one problem left here. That's a good problem, I think. So let me a little bit organize what I have done so far. So let me take this part with me, if hopefully I can fit it here. Yes, to open a little bit of space here. And then I can also move this. Okay, I can put it here now. That's okay. Now let us go to the next problem. Yes. So what is the next problem? It's, let me discuss it here. So here, I don't know if you could find the correct collecting here yourself, but I would say that I realize that I have the difference of two complete cubes here and the last one. And then I have the difference of two complete squares. The first ones gives me this idea of this identity, actually, the difference of two complete cubes, and the difference of two
complete squares reminds me about the conjugate identity. Okay, so let me group them in this way. Number 4, I will write 27a to the 3 minus 8b to the 3. Then I will have minus 9a squared and then positive 4b squared. Again, probably you can see it contains a wrong sign, yes? So I would prefer to take a negative sign out right here. It becomes positive 9a squared minus 4b squared, yes? The reason is that I have a coming first and b coming second. So I just factored this negative out to make a coming first and b coming second in the second group, yes? And then I will use the identity exactly right here. I use the difference of cubes to use it here, and then I use the conjugate identity here. So what can I see is that this becomes 3a, the cubic root of the first one, minus 2b, the cubic root of the second one. And then I will have the first one to the 2, which gives me 9 squared, and the product of the terms with the opposite sign, so it will give me 6ab, with the opposite sign becomes positive 6ab, and the second one to the 2, which gives me 4b squared, yes? And then what I have is minus, the second one is the difference of 2 complete squares, so I can use the conjugate rule. So it becomes the square root of the first one minus the square root of the second one multiplied by the square root of the first one plus the square root of the second one. Now you can see that a new common factor emerges. So I can pull it out now. So then it becomes 3a minus 2b, and then you have 9a squared plus 6ab plus 4b squared, and then you have minus 3a plus 2b. So you see, I pulled 3a minus 2b out. So this one is left from the first group, and this negative sign and this one are left from the second group. But nobody writes these extra pairs of brackets. I multiply it and write it in a little bit more tidy and organized way. So it is 3a minus 2b. Then I will have 9a squared plus 6ab plus 4b squared minus 3a minus 2b. That's of course enough, but if you want, you can write it in this more organized way. So I would prefer to write 9a squared first. No, everything is okay, by the way. So yeah, that's already in the good organized form. Yes. Okay, but you might see that this a quadratic pattern? It is not, yes, because the square root of the first one is 3, the square root of the second one is 2b, and if you multiply by an extra 2, it becomes 12ab, which is not 6ab. So this is not actually a quadratic pattern.
Okay, now we can go to the next method number 5, adding and subtracting suitable terms. Let me read it for you. Sometimes adding some suitable terms and subtracting them can transform the polynomial into a new form of the same polynomial, to which method 4 can be applied to factorize the polynomial. To determine which terms should be added and subtracted could be quite intractable to discover. One needs to practice a lot in order to improve their skill in this regard. And even if you really practice, if the terms involved in the polynomial are too many, probably it's not that easy to realize this pattern, the pattern going on, the terms that we have to add and subtract, okay? Here, I will written 5 examples here for you. These are classical examples in this regard. So I would say 1, 2, and 3 are fairly simple ones, and then 4 and 5 are a little bit harder. But of course, as I told you, these are classical examples in this regard, so I have brought them here for you so that you are familiar with that. You get familiar with these methods. Okay, so I will solve a first one and the second one for you, and I will recommend you to pause the video and try to solve number 3 yourself. Might be you should also be able to guess number 4, but if you don't have any experience for number 5, then it might be very hard. I remember when I was a teenager, my algebra teacher in the high school, Mr. Ramin Munaveri, gave this to us, and I really spent more than 2 hours, and I couldn't discover the terms that I have to add and subtract in order to be able to factorize this polynomial at the end. And then when I saw the solution, when my teacher solved the problem for me, I was really impressed. And so I really liked it. So this is one of those classical examples in this regard. So I want to share that with you. Okay, so now let us do the exercises together. So let me divide this into 2 parts now. Okay, so number 1, you want to see how we can solve this problem. Okay, so if you see here, I have x to the 4, and then I have x squared and 1. Of course, I have 3 terms. This is a trinomial, but this is not probably the quadratic pattern in exactly this form that you see here, but it can be transformed into a polynomial that 3 terms of that polynomial form a quadratic pattern. How? By adding x squared to the polynomial and subtracting that. Yeah, so let me write it for you. So here, x to the 4 plus x to the 2 plus 1 can be written as x to the 4 plus 2x squared plus 1. Okay, then I subtract x squared from it. Yeah, so in this case, this equality is indeed valid, yes, because 2x squared minus x squared is another name for positive x squared. So what I have written here as equality is completely valid. But what is the benefit of rewriting this expression in a more complicated form? If you ask me, is this more simplified than that one? I would say definitely this is the simplified version for this. But remember, the goal is not simplification here. The goal is to be able to write your polynomial as a product. Yes. For that purpose, then you can probably realize that in this case, the first 3 terms will give me a quadratic pattern. So what can I do? I can immediately write it as x to the 2 plus 1 totally to the power of 2. Let us double check. The first one to the 2 will give me x to the 4. 2 times the first one times the second one will give me 2x squared, and finally the second one to the power of 2 will give me 1. And then I have an extra negative x squared, so I will write it down here. Okay? And then you immediately realize now that I have the difference of 2 complete squares, so I can use the conjugate pattern, yes? So then it becomes square root of the first one minus the square root of the second one, multiplied by square root of the first one plus the square root of the second one. And I myself prefer to write it in more organized way, write x squared first minus x second and 1 as a third term, and then the same thing for the other factor as well. Yes. Let me write something with another color here for you. You might wonder, can I continue with the same method and the same logic to factorize this expression a little bit more? So let me tell you why we cannot continue. So assume that you want to factorize x squared plus x plus 1 exactly with the same method. You might think that I can add x to it, it becomes 2x, and then I subtract x exactly the way that I did here, yes. Now I add x and subtract the same x. So this equality is still valid. But why this is good, you can write it as collect the first 3 terms into a quadratic pattern. It becomes x plus 1 to the 2, and then I will have minus x. Of course, you might write this in this form,
which is completely valid. All what I have done here, all of them are valid. So the last step needs that x should be non-negative, because if x is negative, then I cannot square root of it. So now assuming x is positive, every step is valid, then you might think that I had, okay, now I have the difference of two complete squares, so I can use the quadratic rule as a conjugate rule again. So it becomes the square root of the first one minus the square root of the second one, and then the square root of the first one plus square root of the second one. If you ask me, is this expression equal to this expression for non-negative values of x, I would definitely say yes. What I have done here is completely valid. But I will not assume this product, even though it's in the product form, I will not assume this as a factorization of my original polynomial, because these factors are no longer polynomials. And by default, when we say factorize, we are factorizing polynomials, and we assume that the factors involved in the factorization are also polynomials. Yes, so this is not a polynomial, because x plus 1 minus the square root of x, you can write it as x plus 1 minus x to the power of 1/2. And you know that in a polynomial, by definition, the exponents appearing for variables should be non-negative integers. So 1/2 is not a non-negative integer, so it cannot define a polynomial. So this expression does not define a polynomial. So from equality point of view, this equality is valid for non-negative values of x, but I will not consider this as a factorization. So because of this explanation, I will consider this as the final point to this problem. Okay? So let me go to problem number 2. Yes. So problem number 2, it's x to the 4 plus 4. So I have x to the 4 plus 4. So what is the term that I should add and subtract? It's not that hard. Again, the idea is very similar to the previous one. I told you, these are classic examples. So I will write x to the 4, and I will add 4x squared to it plus 4, and then I subtract the term that I added. Yes, now let us check. So what I have written here is exactly equal to this polynomial, yes? Because you see immediately that minus 4x squared and 4x squared are canceled. But what is the benefit of doing that? Probably you know it yourself now. So the first three terms, this one and this one and this one, will constitute a quadratic pattern for me. So I can write it as x to the 2 plus 1 to the 2. Yes, let us double check. The first 1 to the 2 will give me x to the 4. 2 times the first one times the second one will give me 4x squared. And the second 1 to the 2, oh, sorry, it is not 1, sorry. So let me fix it. This is not 1. This is indeed 2. Okay, so the first 1 to the 2 is x4. 2 times the first one times the second one is 4x squared, and the second 1 to the 2 is 4. And then I have minus 4x squared that I can immediately write it in this form, 2x to the 2. And then why this is good, because now you see that I have the difference of two complete squares, so I can use the conjugate pattern, yes? So I can just write it the square root of the first one minus the square root of the second one, and then I will have square root of the first one plus the square root of the second one. I myself prefer to write it in a more organized way. I would write x squared minus 2x first and then 2, and then the same thing for the other factor. So that would be the factorization of this polynomial. So I recommend you to pause the video now and try to solve number 3 yourself. Number 3 is not hard, even though that's also a classic example. And number 4 is a little bit harder, and number 5 is even harder. Okay, so okay, you can pause the video and try to solve the problem yourself. Now I will continue solving the problems. So number 3. So number 3 is x to the 4 plus 4y to the 4. So x to the 4 plus 4y to the 4. Yes. I hope that you could guess what is the term that I have to add and subtract. That term is 4x squared y squared. Yes. I can write it as x to the 4 plus 4x squared y squared plus 4y to the 4, and then I will have minus 4x squared y squared. Yes, so I decided to add this term and subtract the same term, but then these three will form a quadratic rule. So this becomes x to the 2 plus 2y to the 2. Let us double check. The first one to the 2 will give me x4. 2 times the first one times the second one. Oh, sorry, there is a 2 here missing. Okay, 2 times the first one times the second one will give me exactly this term. And the second one to the power of 2 will give me this. But instead of writing 4x squared y squared, I can simply write 2xy to the power of 2. And again, you see that this is the difference of two complete squares. So I can use the conjugate pattern once more. So this becomes the square root of the first one and minus the square root of the second one, and then the square root of the first one plus the square root of the second one. I myself prefer to write it in more organized way in this form, but that's not an obligation. Yes. Okay, now let us go to more tricky problems. So number 4. So let me write it here. Yeah, it's working still. So number 4. It's a little bit tricky to discover the term that you need to add and subtract here. So let me do it for you, and I ask you to try to follow me, the steps. I want you to follow the steps, what's going on. So I would write x to the 5 plus x plus 1. I would add x to the 2 and then subtract the same thing. Okay, so let us see. So I would write x to the 5 minus x to the 2, yes. And then I would write plus x to the 2 plus x plus 1. So you might wonder why on earth I should add that term and subtract that term, minus x squared and positive x squared. So you need to be patient. The only thing that I can answer at this stage is that if you are patient, you need to wait and see it works. Yeah, that's the only reason that I have done that. But how can I discover it for the other problems? I would say there is no specified recipe for that. Yes, so you need to have a lot of experience by solving a lot of problems to be able to do that. Okay, what I want you to do now is just to follow what I am doing, and then try to check the validity of these equalities. Yes, so I hope that you realize that these two are exactly the same, because I have subtracted minus x squared, then I have added x squared to that. So they're exactly the same. But then, do you remember the grouping thing? So now I group these two together, and I group these three together. Yes. So what can I do? I can factor x squared out from the first two. I will get x to the 3 minus 1. Then I can put x squared plus x plus 1 in the same pair of brackets, and I cannot factor anything out because there is no common term for x squared, x and 1. Yes. But now, hopefully, you realize that what is here is the difference of two complete cubes, because another name for 1 is 1 to the 3. Yes. So I have x to the 3 minus 1 to the 3, and then I can use the pattern. So the difference of two cubes. So this becomes x squared. The cubic root, I am writing something for this, and then I am assuming that is 1 to the 3. So the cubic root of this is x minus the cubic root of the second one is 1. And then the first 1 to the 2, x squared, the product of x and 1, which becomes x, but with opposite sign, it becomes positive x. And then the second 1 to the power of 2 is 1. And then you realize why this works now, yes? Because now you see that this factor here and this factor here are the same factors, So I can just factor it out. So it becomes x squared plus x plus 1. And then what is left is x squared, x minus 1. This is, if I pull this out, what is left is here, that I put it here. And then this becomes just simply 1, yes? Okay,
And then what happens, I can write x to the power of 2 plus x plus 1. Then I can have x to the power of 3 minus x to the power of 2. And then I have plus 1. Yes, so that is the end of this problem. So this is written in factorized form. Okay, so now let us go to the last problem of this part. This is actually very challenging. I hope that you can follow what I am writing here. So x to the 10 plus x to the 5 plus 1. So the terms that I need to add and subtract are actually quite a lot. So what I do, I write it in this form. I would write x to the 10, I will add x to the 9 and x to the 8, and I subtract the same two terms. Then I will add x to the 7 and x to the 6, and I subtract the same two terms. Then I will add x to the 5 and x to the 4. Then I will subtract the same two terms. X to the 5 minus x to the 4. Okay, so far, all of these terms are actually canceled, yes, up to here. And then I have only x to the power of 10. So instead of x to the power of 10, I have written this. And then you see that I have an extra x to the power of 5. So I would write it here. I would write it here. And then I start adding and subtracting other variables here now. So I will add x to the power of 3 and x to the power of 2 and subtract x to the power of 3 and x to the power of 2. And finally, I add x and minus x, and then I will have 1. Let us make sure that everything is in order, yes? So you see, from here up to here, all the terms are canceled, yes? One pairwise. X to the power of 10, I need it, I have it here. X to the power of 5, I need it, I have it here. Then again, all the terms here are canceled pairwise. And then I have a positive 1 at the end, which I needed here. So hopefully I could convince you that what I have written, all these terms, this is exactly what you have here. But what is the benefit of doing that? So let me try to somehow convince you. So let me change the colors every time. So I will take this one and this one and this one together. And then I will factor x to the power of 8 out, yes? So what is left for me is x to the power of 8. And then I have x to the power of 2 plus x plus 1, yes? So my goal is to group them in a way that when I pull the common term out, x squared plus x plus 1 appears as a common factor to all the polynomial, yes? So for example, by having this in mind, so let me change my color now. So for example, I go to the next one. I want to factor minus x7 out from here, and from here. Yes, so I factor minus x7 out. And then what is left for me is x to the power of 2 plus x plus 1 again, yes? So far, so good. You see, now this is a common term appearing here. Okay, now let me change the color once more now. So these are very similar, so let me write this one. So now I want to factor x to the power of 5. Yes, I want to factor x to the power of 5 between this expression and this expression and this expression, yes. So if I pull this out, it becomes x to the power of 5, and then I will have x squared plus x plus 1, yes. Then I want to factor minus x to the power of 4, so let me mention it for you here. So minus x to the power of 4 between these two terms. So minus x to the power of 4, minus x to the power of 5, and minus x to the power of 6. So if I pull minus x to the power of 4 out, then I will have exactly x squared plus x plus 1 again. So you see, every term now has this common factor x squared plus x plus 1 so far. Okay, now let us see what happens. So then I have these terms. So let me change the color here. So here I will have this term, yes, this term, and this term, and this term, yes? So I can factor x3 out. So what is left is that I have positive x to the power of 3, then I will have x squared plus x plus 1, okay? So now what is left for me, I can factor minus x out, yes, from these terms. So let me change the color. So I will take minus x out from here and here and here. Yes, so I will get minus x, and then I will have x to the power of 2 plus x plus 1. And hopefully what is left is exactly x squared. Yes, you see what is left is this one and this one and this one. Yes, so this becomes exactly x squared plus x plus 1. Yes, and then if you check, we considered everything here. Yes, everything is actually considered now. So then what can I do? I can factor x squared plus x plus 1 out, and what is left for me is x8 from the first one, negative x7, positive x5, negative x4, positive x3, negative x, and then finally positive 1. Yes, and this is the factorized form of this expression. So this is a classic example showing that this method could be extremely hard to guess which terms to add when which terms to subtract. So yeah, but it is a little bit fun actually. So this is a hard problem. Okay. Now we go to the next actually method, which is actually the last thing that I want to discuss in this video. Okay. So now we go to the last method that I want to cover in this lecture. And then you are more or less familiar with this method when I was talking about one of the methods that I introduced when I was teaching you how to factorize a quadratic polynomial. Yes. So you remember you break the middle term into the sum or sub difference of two terms in an appropriate way, and then group them and then factorize them separately, okay? This turns out to be a more general trick, not only for the quadratic polynomials, but for a number of polynomials. And I have written for you 4 examples here so that I will try to solve them for you and then describe them for you. Okay, so the first example, of course, is a quadratic polynomial. Yes, so let me divide this into smaller piece here. Okay, now I have 2x squared plus 5x minus 3 that I want to factorize it. So number 1. So if you remember, when I was teaching about how to factorize the quadratic polynomials, I taught you a trick. I told you that you ask yourself, I need 2 numbers whose sum is equal to 5 and whose product is the product of these 2 numbers. So let me write it here. So you would ask yourself, I need 2 numbers whose sum s is equal to 5, is equal to 5, and the product is the product of these 2 numbers, which is minus 6. Okay, what are those numbers? The sum is supposed to be 5, the product is supposed to be negative 6. So it is a positive 6 and negative 1. Yes, so the numbers that are involved are positive 6 and negative 1. These are the numbers. If I add them, it becomes 5. If I multiply them, it becomes negative 6. Yes. Okay, and then I told you that using these numbers, you can break this into two parts, this middle term. So 2x squared plus 5x minus 3 can be written in this form. 2x squared, instead of positive 5x, you write positive 6x, negative 1x, yes? So it becomes positive 6x, negative 1x is just simply x, and then I have minus 3, yes? Now, what I do is to do this. I take these two together, and I will take these two together, yes? And then here I can factor 2x out. Then what is left is x plus 3 from the first group. And in the second group, I factor a negative sign out. So it becomes negative x plus 3, yes? So I pulled this negative sign from here and here and wrote it here. So this becomes x plus 3 and x plus 3. So what can I now do? I can just pull this x plus 3, which is a common factor now, out, and 2x minus 1 is left. So you see, that was the method that we already learned. But what we did here, we actually broke this, we decomposed this middle term into the difference of two terms, 6x and x, yes? And then we were able to group them and factorize them. So this is, for this specific case of quadratic polynomial, this is more or less an algorithm that help you to recognize these numbers that you have to break the middle term into the sum or difference of those two numbers. But for the other polynomials of higher degrees, there is no general strategy for tackling the problem. So you need to actually improve your skills by solving more problems. Okay, so for example, let me start doing number 2 for you. So number 2 is, I would write it here. So you see it's x to the 3 plus x to the 2. Instead of this minus 1, I write minus 1 minus 1. Yes. So I broke this minus 2 into the sum of two numbers, minus 1 and minus 1. But you might wonder what is the benefit of that, or you might be able to guess yourself. I group them in this way. I take x to the 3 and minus 1 together. I take x to the 2 and minus 1 together. Okay, so let me write it down for you. So it becomes x to the 3 minus 1 plus x to the 2 minus 1. Okay, I hope that you can realize that this is the difference of two complete cubes. One is just 1 to the 3. So instead of 1, you can imagine that you have 1 to the 3. So that is the difference of two complete cubes. And instead of this one, you can imagine that you have 1 to the 2. And then you have the difference of two complete squares. Okay, so I use the identity of the difference of two cubes for the first group, and the identity of the conjugate identity for the second group. So the first one becomes x minus 1, x to the 2 plus x plus 1. So what I have written here is, because this is the difference of complete cubes, the cubic root of the first one minus the cubic root of the second one, and then I have the first one to the 2, the product of these two with the opposite sign, and then finally the second one to the power of 2. And the second one is, of course, the conjugate rule. Then you realize that actually I have a common factor now, so I can pull it out. So then it becomes x minus 1. What is left from the first one is x squared plus x plus 1, yes? And what is left from the second one is just x plus 1, yes? So if you want, I can put them in brackets to see them better. So I pull this x minus 1 out. What is left from the whole term is just this one. And here, what is left here is just this one. But as I told you that nobody will leave this like this, we simplify the mathematics. I remove the unnecessary brackets. So it becomes x squared plus x plus 1. The next one becomes x plus 1. Then you immediately can write it as x squared. And then you have this x, and this x becomes 2x. And then you have positive 2 at the end. this 1 and this 1 becomes 2. So that's the factorization of this polynomial. So for example, you can pause the video now if you want. You can give it a try to the number 3. Number 4 is a little bit more tricky, okay? And then you can play back the video again and check your answers against mine, okay? So here, let me see what can we do. So based on my experience, I more or less immediately realized that I can break this middle term minus 5x into minus 3x and minus 2x. Of course, minus 5x can be written as a sum of two pairs in infinitely many ways, but only this one will work. Yes. So what I want to write is that I would write this in this form. I would write this becomes equal to 3x to the 3. Instead of minus 5x, I put minus 3x and then minus 2x, then I will have positive 2. So what you see here is minus 3x minus 2x is the same as minus 5x. Yes. So this equality is indeed valid. And now what can I do? I can use grouping things. So I can take these two together and I can take these two together. Yes. So what can I do now? I can factor 3x from the first two out, then I will be left with x squared minus 1. From the second group, I do not factor 2, I factor minus 2 because I need x to be positive and 1 to be negative. Okay, but so far, this is not a common factor because this is x squared minus 1, but this is just x minus 1. But based on your experience, now you immediately realize that x squared minus 1 is a conjugate pattern. So you can write 3x, and then you can write x minus 1, x plus 1, and then you have minus 2x minus 1. Then you immediately realize the factor that you were looking for, which is common to both terms, is actually both groups, is actually x minus 1. So what I do, I pull it out, x minus 1. And then what is left from the first one, x minus 1 is pulled out. So 3x multiplied by x1 plus 1 is left. So then it becomes 3x multiplied by x plus 1. And then what is left here from the second group is just minus 2. Okay? Then I will multiply and simplify the second factor. So this becomes x minus 1 times 3x squared plus 3x, and then I have minus 2. Okay, and then you cannot continue factorizing this anymore. For example, how we should know that the second degree polynomial here cannot be factorized more. And the reason is that, for example, you can immediately calculate the delta for that. So this becomes 9 minus 4 times 3 times minus 2, which is 33, yes? So yes, yeah, that's correct. And then if you find the roots, so the roots are minus b plus and minus a square root of 33 divided by 2 times a, which is 2 times 3, and that is 6. And then of course, if you remember, you can write 3x squared plus 3x minus 2. You can write it in this form, 3 times x minus minus 3 minus the square root of 33 over 6, and then x minus minus 3 plus the square root of 33 over 6. Even though this equality is indeed correct based on the theorem that I proved in the last session, but I will not consider this as a factorization of my polynomial, because you see that the numbers involved are irrational numbers. And by default, I want to factorize it on the set of integers. Okay, so even though this equality is correct, but I will now continue this one. So I will, let me cross this over. We don't need to go through this, yes? So that would be our final step in this factorization. Okay, so let me go to the next problem and the last one. So number 4. Number 4, I can see that in number 4, first of all, you see that A is common to all of them. If you remember from the first lecture for factoring polynomials, factoring A out has the priority over all other methods. Yes, because A is common to all the terms in the polynomial. So I will take this A out. Then I will have a to the 3 plus 6a squared plus 11a plus 6. Okay? Then, of course, you need a little bit of experience to be able to see what breakings, what decompositions can happen here so that I can solve and factorize my polynomial. I did some trial and error before writing this question actually. So now this is why I know exactly what to do, but let me share it with you now. So instead of 6a squared, I just write a squared plus 5a squared. Instead of 11a, I put 5a and 6a, and then I will have 6 at the end. It's not that easy. It took me a while to be able to discover this pattern. Okay, but I want you to understand, what I expect you to is to understand that this is a valid equality. So this a is this a3 is this a3, and then a squared plus 5 squared is indeed 6a squared, and 5a plus 6a is indeed 11a, and then 6 is the same thing. But what is the benefit of doing that? I can do grouping. I can take these two together, I can take these two together, and I can take these two together. Yes, so what can I do? I can just copy and paste this a part. Between these two terms, I can factor a squared out. So this becomes a squared, a plus 1. And between these two, I can factor 5a out. It becomes 5a. Then I will have a plus 1. And between the last two, I can factor 6a out. So that is a good method. This is a good decomposition, and this is a good grouping, because now you can immediately see that a plus 1 appears, yes, as a common term. So now I can factor it out. So this becomes a times a plus 1. And what is left here from this, a squared is left. From this, 5a is left. And from this, 6 is left. So it becomes a squared plus 5a plus 6. But hopefully now you have enough experience of factorizing these type of polynomials. So this, I want to factorize it using the common factor identity. So what I want to give the role of the common factor to a here. Then I will ask myself, can I find two numbers whose sum is positive 5 and the product is positive 6? That's very easy. Yes, one of them is positive 2 and the other one is positive 3. And that is the full factorization of these polynomials. Okay, so I hope that you enjoyed the video and you have learned more techniques and tricks to factorize the polynomials. I will continue this topic for next week. And then, as I told you before, I will put a link that takes you to the PDF file containing some problems related to these materials that I covered here. And I will also put the link to the PDF file of this lecture notes, including the solutions, and one without solutions. And then I will also put the GoodNotes version of both lecture notes without solutions and solutions. Okay? Until the next video, thank you and goodbye. Thank you.